Okay, so here are our lesson 5-3 notes covering the sum and difference identities for cosine. Now this is all based on a common misconception among high school students. If we're looking at the cosine of angle A minus angle B, that is not equal to cosine A minus cosine B. Students love all the time to just think they can drop parentheses. We can't do that here. In fact, the cosine of A minus B is the cosine of angle A times the cosine of angle B plus the sine of angle A times the sine of angle B. And I know it's very common to say, well, okay, great, who cares? My calculator can do that. But you know, math teachers, we absolutely love to make you do stuff without a calculator. So for instance, let's say that I wanted you to, without using a calculator, to find the cosine of 15 degrees. Now, we have on our list of things that we should have completed by this point in trigonometry, I've already completed a unit circle. So let's pull that up here. The unit circle contains all kinds of helpful information. The basic point of it, though, is that since the radius is equal to 1 unit, these points around the outside have the coordinates cosine theta, sine theta, where theta is the positive rotation from the x-axis. So you see each line is labeled in both radians and degrees. We know, based on this reference item, the sine and cosine, the cosine and sine, of every single one of these angles that's listed. For instance, the cosine of 45 degrees is root 2 over 2, because that's the first coordinate in that point. The sine of 120 degrees is root 3 over 2 because that's the second coordinate in that point. So if we know all of these angles and we know these rules about cosine difference identity, then we can find two numbers on the unit circle that subtract to 15 degrees, such as 45 minus 30, which allows us to write this as the cosine of 45 minus 30, and then follow this pattern, which would mean that the cosine of 15 degrees would equal the cosine of 45 degrees times the cosine of 30 degrees plus the sine of 45 degrees times the sine of 30 degrees. Now if we go and pull those values from the unit circle, the cosine of 45 degrees is root 2 over 2. The cosine of 30 degrees is root 3 over 2. The sine of 45 degrees is root 2 over 2. And the sine of 30 degrees is 1/2. We don't need a calculator to do that calculation. Root 2 times root 3 would be root 6 over 2 times 2, which is 4, plus root 2 times 1 is root 2 over 2 times 2, which is 4. Those fractions have a common denominator, meaning our final answer would be to combine the numerators, which they don't even really combine, so we just write root 6 plus root 2 over 4. That is the exact value of the cosine of 15 degrees, and we did not need a calculator to do that. We just needed our unit circle. There are actually two of these, one for the sum of two angles and one for the difference of two angles. So the sum identity for cosine is cosine A times cosine B minus sine A sine B. The difference identity has almost exactly the same pattern. It is the cosine of A times the cosine of B plus the sine of A times the sine of B, which is a little bit counterintuitive because the sign in here is the opposite of the sign in the identity. This is a plus, so this is a minus. Otherwise, it's the same pattern. Cosine, cosine, sine, sine. Cosine, cosine, sine, sine. That's a negative, so that's a positive. Again, the whole point of this slide is so that we have this as a reference item. You are not expected to memorize these identities. They will be provided to you. You just need to know how to use them. So let's practice using them. Without using a calculator, find the exact value of the expression cosine 75 degrees. Well, again, 75 degrees does not appear on our unit circle. But you know what does are 30 and 45, which add to 75. So what we're going to do is we're going to follow the pattern for our sum identity for cosine, cosine of A plus B, which would be cosine A, cosine B, minus sine A, sine B. So that would be, if we follow that pattern, the cosine of 30 times the cosine of 45 minus the sine of 30 times the sine of 45. So we're going to go to our unit circle and find those values. The cosine of 30 is root 3 over 2. The sine is 1/2. Cosine of 45 is root 2 over 2. The sine is root 2 over 2. So we go in here and we plug in those values. That would be root 3 over 2 times root 2 over 2 minus 1/2 times root 2 over 2. So we're going to start to see some answers that look very, very similar to each other. Root 6, because root 3 times root 2 is root 6, over 4, 2 times 2, minus root 2 over 4 is almost exactly the same answer we saw on that previous example, except now it's a subtraction sign in the middle instead of an addition sign. Now we can make that a little bit harder if we put the angle in radians. However, everyone in here has already shown that they should know how to multiply by 180 degrees over pi radians to convert, which would cause the pi's to cancel and allow us to come up with the value of negative 15 degrees. So this says negative 15 degrees. So feel free to convert from radians to degrees. There's no reason to leave it in radians. As for the value itself, we need two values from the unit circle that subtract to negative 15 degrees. And it doesn't matter at all which two you use. You can do 120 minus 135. You can do 210 minus 225. You can do, the easiest one would be 30 minus 45. It doesn't matter at all which one you use. What's important is that you're following the correct pattern, which would be cosine A, cosine B, plus sine A, sine B. So this would be cosine of 30, cosine of 45, plus sine of 30, sine of 45. Go to the unit circle. The cosine of 30 is root 3 over 2. Cosine of 45 is root 2 over 2. Plus, the sine of 30 is 1/2. The sine of 45 is root 2 over 2. Again, these answers are going to keep looking very similar. So we multiply, and then we add those together. Root 6 plus root 2 over 4. The 75 degree increments and the 15 degree increments are made up of root 6, root 2 over 4. It's the same for every single one of these. Okay, we can also use these identities by using the other side first. For instance, if we look at this particular example here, we have the cosine of an angle times the cosine of a different angle, plus the sine of that first angle times the sine of the second angle. Oh, shouldn't be plus, should be minus. My mistake. Let's change that to a minus. That pattern is the same pattern as the cosine of A plus B. That allows us to rewrite this as the cosine of 87 plus 93. Well, 87 plus 93 is 180 degrees. And guess what? That value is right on our unit circle. The cosine of 180 degrees is negative 1. Done. Moving on. Let's do another one of those. Okay, here we have the cosine of an angle. Let's call 110 will be our A, times the cosine of a second angle, plus the sine of our first angle, times the sine of our second angle. That is our difference identity. So that should be written as the cosine of 110 minus 50. 110 minus 50 is 60 degrees. That is on our unit circle. It is root 3 over 2. Okay, we can do this with radian measures as well. So this would be, let's just convert everything from radians to degrees. Pi over 6 is on our unit circle. That's 30 degrees. Pi over 3 is on our unit circle. That's 60 degrees. So what this is saying is the cosine of 30 times the cosine of 60 minus the sine of 30 times the sine of 60. Well, again, that is one of our two patterns. If this sign is a minus, then that is equal to the cosine of A plus B. So we would rewrite this as the cosine of 30 plus 60, which would be the cosine of 90 degrees, which is on our unit circle. The cosine of 90 degrees is 0. Cosine of 90 is 0. Sine is 1, cosine 0. Okay, that brings us to the last part of this is new information, and not really even new information. This is information we've had before, but we didn't do much with it before. And that are the cofunction identities. There's a reason why our 6 trig functions are so closely related to each other in names. The cosine of 90 minus theta degrees is equal to the sine of theta degrees. Same for the other direction. The sine of 90 minus theta is equal to the cosine of theta. That's not a surprise, or it shouldn't be. Sine, cosine. They're co-functions. Sine and cosine. The same pattern applies to secant and cosecant, tangent and cotangent. So we should be able to finish this out relatively simply here by simply rewriting the left side as the cofunction on the right. So the tangent of 90 minus theta is the cotangent. The cotangent of 90 minus theta is the tangent, because again, these are cofunction pairs. Sine and cosine, secant and cosecant, tangent and cotangent. That's why they're named that way. So let's talk about how one way that we could use that is to solve trig equations. So here we have a trig equation that says the cotangent of theta is equal to the tangent of 25 degrees. Well, those aren't the same trig functions, so we can't just like drop them or anything. But fortunately, our cotangent or our cofunctions identities say that the cotangent of theta is equal to the tangent of 90 minus theta. So if we plug that in for the left side, sort of like we did in the first two sections of the chapter, we can replace those. Well, that means that these two angles in this expression, 90 minus theta and 25, have to be equal in order for their tangents to be equal, which allows us to state that 90 degrees minus theta is equal to 25. And then we simply solve that equation. Now there's a couple ways to actually solve it. My favorite is to just add theta and subtract 25 from each side, which would give me 65 degrees equals theta. Now I had somebody in class ask me, well, how is that 1? What other answers are there? And the answer is any angle that is coterminal to 65 degrees would also be an answer to this question. In fact, any angle that is in the third quadrant and has a reference angle of 25 degrees would also work, I think. That may not be true. Let's just stick to the reference angles. There are definitely an infinite number of answers to this. So same thing on letter B. We're going to replace sine with its cofunction, cosine 90 minus theta. That equals the cosine of negative 30 degrees. Because those both say cosine now, I can drop that and write this as 90 minus theta equals negative 30. then all I have to do is solve. So if it's me, I'm going to be adding 30 to each side and adding theta to each side, which would solve it for theta and give me an answer of theta is 120 degrees. Again, probably not the only answer, but it is an answer. Okay, that brings us to the last slide, and this is a, quote, more advanced problem, but it's really not. What it is drawing on previous knowledge. We did all kinds of problems exactly like this one back in chapters 1, 2, and 3. It's based off of the definitions of our various trig functions. We are asked to find the cosine of s plus t. Well, according to our pattern, that is the cosine of s times the cosine of t minus the sine of s times the sine of t. Now we're only given, and this is what makes this problem supposedly harder, is we are only given the sine of s and the cosine of t. That's all we're given in the directions. But that's all we need. Because if we know the sine of s, we can find the cosine of s. So our first step in this process is to find the cosine of s. Okay, and I'm going to put parentheses around s just so you don't think it says okay, it's the cosine of angle s. What we need to do is we need to draw on our knowledge. The sine of s is 3 over 5. Well, we should know that sine, by definition, is y over r, which means y equals 3 and r equals 5. We should also know that for every angle, every point, x squared plus y squared is equal to r squared. This is loosely based on the Pythagorean theorem. So if we plug in what we know, we can find x. So that's 3 squared for y, 5 squared for r. Again, I guess in theory I should put that in parentheses, but it shouldn't matter because the numbers are positive. So we'd have x squared plus 9 equals 25. We would subtract 9 from each side, which would give us x squared is 16. And then we would take the square root, which would give us plus or minus 4. But we need to know whether it's positive or negative. That's told right here where it says s and t are in quadrant 2. So if angle s is in quadrant 2, x is negative. So that means x is negative 4, and the cosine of s, which is x over r, is negative 4 over 5. So now we know our third value. We now know the cosine of angle s is negative 4 over 5. So we're going to do that process one more time. Call this step 2. And we're going to use it to find the sine of angle t. We start with what we know, which is the cosine of angle t is negative 12 over 13. And we draw on our previous knowledge, which tells us that that cosine value is x over r. So x is negative 12 and r is 13. And since t is also in quadrant 2, it would make sense that x would be negative. Remember, r is always positive. So if you're wondering why does the negative go with the top, it's because r is the distance from the origin. That has to be a positive number. Same deal, we're going to plug into x squared plus y squared equals r squared. The only difference being that now we're solving for y instead of x. So we have negative 12 squared plus y squared equals r squared. That would be 144. Oh, it should have been 13 in for r squared. My mistake. Let's fix that real quick. So negative 12 squared plus y squared equals 13 squared because r is 13. So 144 plus y squared equals 169. Please note you should never get a negative number in this step ever. because when you square a negative, it becomes positive. So whether it's positive or negative up here is irrelevant. Here, it should be positive. Subtract 144 from each side gives you y squared equals 25. Take the square root. Y is either positive or negative 5. Now again, we know that angle T is in quadrant 2. And in quadrant 2, y is positive. You don't believe me? Go back and look in your notes for chapters 1, 2, and 3 where we've built all that reference material. If y is positive, then y is 5, and the sine of angle T, which is y over r, would be 5 over 13. So we're going to plug in that value for sine of T, 5 over 13. So that is our next step. Now that we know all 4 of our values, which we got the last one from our directions there, we're going to plug them in. The cosine of S is negative 4 over 5. Cosine of T is in the directions, negative 12 over 13, minus. The sine of S, which is in the directions, is being 3/5. And the sine of T, which we just found, is 5 over 13. Multiply those fractions together would be 48 over 65 minus 15 over 65. And I know that this can be reduced, but I don't want to reduce it because I'm going to have to combine these two fractions. So I'm going to want them to have a common denominator, which they do at 65. So there's no point in reducing this fraction yet. 48 minus 15 would be 33 over 65. And at this point, I check to see if that can be reduced. But 33 is only divisible by 3 and 11, and 65 is not divisible by either one of those numbers. So that would be my answer, 33/55. That completes our notes for lesson 5-3.